Hello everyone, welcome back to Native Engineering once again. We are doing another exercise on shock load. The exercise that we are doing reads as follows. A load of 30 newtons falls through a height of 100 millimeters onto a collar at the end of a rod. The rod consists of two round bars, one with a diameter of 30 millimeters and 500 millimeters long. The other section of the bar has a diameter of 50 millimeters and a length of 1 meter. Both are made of the same material, and the Young modulus of elasticity is 209 gigapascal. Calculate the instantaneous maximum stress in the bar. Number 2, calculate the total instantaneous extension. Number 3, calculate the total instantaneous strain energy. Number 4, calculate the final extension after impact. So this is the diagram that we have. Notice that now we are having an object with two cross-sectional areas. We're having this labeled number 1 and with a diameter of 50. And then we have number 2 with a diameter of 80. The object that is falling is this object, and it will fall to this collar, and then it will cause this strain. The extension, the total extension will be the product of x1 plus x2. We're given the Young's modulus as 209 gigapascal, and we're given the weight as 30 newtons, and then we are given the length number 1 meter, length number 2 is 500 millimeters. I have to copy this object, this diagram, because I am going to erase it. So we are going to start attempting the questions. Question number 1, which will be 7.1. They say calculate the instantaneous maximum stress in the bar. The maximum stress will occur on the section with the smaller cross-sectional area. Stress is given by force divided by the area. This one we know we have to calculate for the force. So that is where I am going to start. We are going to use the formula W H plus X T. It's equals to half of x f times the total extension. We know that this will be equals to x1 plus x2, and we also know that x is equals to f l divided by a e. So we are going to say the total extension is equals to FL1 divided by A1E plus FL2 divided by area 2 times E. The force and the Young's modulus will be the same. Therefore, we are going to take them as common factors, which will be times, in bracket, length number 1 divided by area number 1 plus length number 2 divided by area number 2, close of the bracket. And then we are going to substitute. The force we do not have, that's what we are looking for. The Young's modulus, it's 908, it's 209 times 10 to the power of 9, it's giga. In bracket, what is length number 1? It's 1. Divided by the area, which is pi, divided by 4 times 0.05 squared plus 0.5 rather, which will be the length number 2 divided by the area. This is pi, could be better, times 0.03 squared, close the bracket. And then the answer that I got here is equals to 5.821 times 10 to the power negative 9 F. So let's erase this. Now we have the value for the total extension. This will equate to the total extension. We come back to this equation. I want to take this W to the other side. Therefore, I'm going to divide both sides by W, and we're going to end up with a formula like this. H plus XT, it's equals to F XT divided by 2W. And then we substitute. Our H is equals to what? 0.1. Our total T is equals to this, which is 8.821 times 10 to the power of negative 9 F. It's equals to F squared 5.821 times 10 to the power negative 9 divided by 2 times W, which is equals to 30. This will give us 9.702 times 10 to the power negative 11. So I'm going to say 9.702 times 10 to the power negative 11F squared is squared here, sorry, minus 5, let's erase this, but I already have it now. Point 821 times 10 to the power negative 9 minus 0.1, and then this will be equals to 0. Take this to the top. Our quadratic formula, it's minus b plus or minus, we're going to use the positive root, the root of b squared minus 4ac divided by 2a. And then we are going to substitute. Is negative 5.821 times 10 to the power negative 9. I'm going to use the positive root. The value of p, again, negative 5.821 times 10 to the power negative 9. Negative 4, and then it will be, seems like I want this. Let's move this to it will be times a, which is 9.702 times 10 to the power negative 11 times c, which is negative 0.1 divided by 2 times A, which is 9.702, times 10 to the power negative 11. And then from here I got my answer is 32.135 kilo Newton. Remember, the force is not what we were asked for. We were asked to calculate the maximum stress in the bar, the instantaneous maximum stress in the bar. Therefore, we have to calculate for the stress after getting the force. And then the stress is given by what? Force divided by area. And then our force is 32.135 times 10 to the power 3 divided by the area, which is d pi, divided by 4. We're going to use the small diameter, which is 0.03 squared, because we're looking for the maximum stress rather. And then I got our stress as 5.462 megapascal. This is what we are asked to calculate. And then from here we are going to go to the next question, which is 7.2. They say calculate the total instantaneous extension. So I'm going to erase this. Seven point 2. We are looking for total extension. Remember, we have an equation like this times, we got it in terms of F. But now we do have the value of F, so we can put F here and get the total extension, which will be 5.821 times 10 to the power negative 9, and the value of F, we got that it is equals to 32.135 times 10 to the power 3. And then the final answer, I got that it is equals to 0.187 times 10 to the power negative 3 meters. Then we go to the second question, to the next question, 7.3. Calculate the total instantaneous strain energy. Strain energy is given by what? Half force x t. All of this we have the force times 10 to the power 3 times 0.187 times 10 to the power negative 3. Therefore, our strain is equals to 3.005 joules. And then we go to the last one. They say calculate the final extension after impact. No final extension is associated with gradually applied load. Therefore, our extension will be given by the weight, length number 1, divided by A1E plus weight in length number 2 divided by A2E. This is from the equation. The total length is equals to change in length number 1 plus change in length number 2. So this is change in length number 1, this is change in length number 2. The weight and the Young's modulus, they are common factors. We have length number 1 divided by area plus length number 2 divided by area. Area 2 here is area 1 here. And then from there, we substitute. It's 30 divided by 209 times 10 to the power of 9 times length number 1, which is 1, divided by pi divided by 4 times 0.05 squared. Move this. Plus this is, then we say length number 2, 0.5 divided by pi divided by 4 times 0.03 squared, close bracket, and then this. This will give us an answer of 1.746 times 10 to the power negative 7, which is our final extension, the extension after the impact due to the gradually applied load. And that's how we go about answering this question. See you on the next one.